Let's use the modal diagonal form in order to solve for the time response of a system. So we'll begin by specifying our system in traditional linear terms. X dot equals ax plus bu, y equals cx. Taking this form of the equation, we can now write the matrices that make up our particular example. So in this case, the A matrix is 0, 1, 0 in row 1, 0, 0, 1 in row 2, and minus 18, minus 27, and minus 10 in row 3. The B matrix, 0, 0, 1, and the C matrix is just a row, 1, 0, 0. I've written it here in its transpose form. So you can write now each of our individual differential equations for x dot 1, x dot 2, x dot 3, but we're going to keep them in this matrix form because it's a terse representation of the system. And so I want to know two things about this system. The first thing I'd like to know, what is the modal representation? So I want to take this and put it in modal canonical form. After I have it in modal canonical form, I want to find out for some impulse response, delta of t, what is the zero state response? The zero state response is where x of 0 is equal to 0. So let's go ahead. First of all, the first thing that we're going to do is calculate the eigenvalues of the system. So if you can do this on your calculator, you can just input the matrix A into your calculator and tell it eigs, and it'll return your eigenvalues. But for the sake of completeness, I'm going to show you how to compute that here, in case you've forgotten. So the eigenvalues are computed by finding the determinant of some lambda I minus A. And when we find the determinant, we're looking for values of lambda such that lambda sub I minus A is equal to 0. So we'll go ahead and start by masking the first lambda in corner 1, 1, and then calculating the determinant here. So that gives us lambda times the quantity lambda times lambda plus 10, so this diagonal here, and subtract away 27 times minus 1, this diagonal here. That, of course, is 27 positive. So that's our first term, and then we subtract this mask times this product minus this product. So you can see that this is minus a minus 1 times 0 minus a minus 18. So a bunch of our negative signs cancel. We multiply through a bunch of pieces that we had already. I'm going to just remove these little specks of red here so they don't clog a version of this if I decide to post the notes. And then plus 0, because the final term that we have here, 0 times whatever these determinants were going to be, is going to make it just equal to 0. So now we multiply through the lambdas, and we add back the 18 that we have here, and that gives us lambda cubed plus 10 lambda squared plus 27 lambda plus 18. So if you haven't already used your calculator to calculate the eigenvalues directly, here it's asking you now, let's use our calculator to find the roots, lambda, values of lambda that are going to satisfy this equation equal to 0. So, a little bit of algebra later and a little bit of calculator later, we get 3 values for lambda, minus 1, minus 3, and minus 6. So these are the eigenvalues of the matrix A, and we're going to use these to calculate the eigenvectors. So just as a reminder, the eigenvectors are each eigenvalue times I minus A times some vector e sub I equal to 0. So our goal is to find these e sub I vectors based on the eigenvalues lambda sub I that we already have. And because we have 3 eigenvalues, we'll have 3 eigenvectors. And just as a reminder, we're doing this so that we can produce our P inverse matrix. The P inverse matrix is going to allow us to write our system in modal diagonal form. So each of these e sub i's for E1, E2, and E3 we're going to put in columns, and that's going to give us P inverse. So as we go, I'm going to go ahead and reproduce A here so that we can see how we're coming up with these various systems of equations in order to solve for each e sub I. So let's start with lambda sub 1. So lambda sub 1 times I minus a should be equal to 0 after we multiply it by this eigenvector e1. So lambda sub 1 is equal to minus 1. Therefore, lambda sub 1 times I minus a produces this matrix. Minus 1, minus 0, obviously. Then 0 for the second element, minus 1 gives us minus 1 here. And then our third element is going to be 0. So you continue on down through row 2 and row 3. And again, we've left e1 as a variable here. So the lambda 1 times I minus a part should be fairly straightforward. What's less straightforward is how do we come up with e1 in order to satisfy all three of these equations. Well, it shouldn't be that hard because we know that lambda sub 1 is an eigenvalue. So we know that if we can solve it for one of the equations, it'll probably work for the others. But it's tricky when you have a 0 here. So let's see what we should do. So for example, I can know by looking at the first row that if I just randomly or arbitrarily choose 1 for row 1 of e1, that I now have a negative 1, and I need to add 1 to that in order to make it come out to be 0. And so I'm going to multiply column 2 of the first row times minus 1, which is going to give me minus 1 plus 1. And then seemingly I can set row 3 of e1 to be anything that I like. But that actually won't work for row 3. If I look at row 3, now I'm multiplying 18 times 1, multiplying 27 times minus 1. So I need to multiply 9 by something in order to make this actually turn out to be 0. So I'm just going to call that something x. And then I can write 18 minus 27 plus something equals to 0. Well, that something actually turns out to be 9. So x is 1, and that gives me my first eigenvector e1. We're going to do this for each of the eigenvectors and each of the eigenvalues. So for lambda 2 equals to minus 3, I end up with this representation of lambda 2i minus a, and I'm going to do a similar thing for e2. So from row 1, I can choose 1 again here for minus 3, and minus 1 again here, which is going to give me minus 3 plus 3. But then I need to do something with the third value. So because I have a 0 here, I could choose any number that I want to satisfy this equation. Let's go ahead and make sure these arrows go away. Almost. So 1 and then minus 3, and now I get to choose the third value, x. So 18 minus 3 times 27 plus 7 times x should be equal to 0. Or minus 63 plus 7x should be equal to 0, aka x would be 9. So that gives me a nice result here. So 1 minus 3, 9 becomes the second column of p, and let's do now the third column. So for lambda sub 3 equals minus 6, I produce lambda 3i minus a. So 1 and minus 6 allows me to satisfy row 1, and I can use row 3 again to come up with the final value. I could also use row 2 here, because for row 2 I would be able to see that minus 6 times 1, or minus 6 times 6 plus something times minus 1 should be equal to 0. So it should be pretty trivial to see what that is here, but I've used row 4 again. So 18 minus 162 plus 4x should be 0. 4x is 144, or x equals 36. So this allows me to write E3, which is the third column of P inverse. So now I can recreate P inverse here, and using my calculator, produce P by inverting P inverse. So P turns out to be this fairly complicated but straightforward matrix. And so now I'm going to use P and P inverse to write my system in modal canonical form. So the modal representation, x bar dot equals a bar x bar plus b bar u, y equals c bar x bar. So I need to calculate b bar and c bar. So b bar is calculated by multiplying p times b. So we can see here that b only has an element in row 3, and it only has one column. So I'm actually only interested in the third column of P. That makes B bar pretty easy to calculate because I don't need the first two columns. And C bar, turns out I only need the first row of P inverse in order to calculate C bar, because column 2 and column 3 of C are both zeros. So C bar is really easy to compute. It's just 1, 1, 1. So with this I can write the modal representation. And y, of course, is equal to C bar times X bar. Y is the same observer I had before, or the same observed matrix that I had before. In this case it's still just a scalar because it's a 1 by 3 times a 3 by 1. But the value for y is the same because we can choose an infinite number of states. We just happen to choose a state x bar so that A was diagonal. So this gives us the modal representation. So now that I know the modal representation, I can check the zero input when u of t is equal to delta of t. So the solution to this, by the way, is the same as it always was before. It's just that we have a zero, sorry, it says zero input there, but this is actually zero state. So we're checking for the zero state response when we have an input of delta of t. So when this happens, this integral becomes really easy to do. And e to the a bar of t minus tau was also really easy to compute. So x bar of t is just this diagonal e to the minus t, e to the minus 3t, and e to the minus 6t, times b bar, which is 1/10 minus 1/6 and 1/15. So with this in mind, we just have a vector here of x bar of t. This will give us the solution to x bar at any time t in the future for zero initial condition. So now we can calculate the response, y, based on the fact that we've already computed c bar. So c bar was equal to 1, 1, 1. X bar was equal to what we just calculated before. So now we can produce y of t as the sum of each of these three component parts of the x bar vector. So that's a pretty easy way to calculate y of t. And this, in fact, is the zero state response for an input u of t equal to delta of t. So there's a couple of important things to notice here. The first, did we need e to the at, the actual e to the at? No, because we had e to the a bar of t. Did we need to calculate x of t in our original state space x? No, because we had x bar of t, and we were able to get y of t from x bar of t. So as long as we weren't asked for the x of t solution, we didn't need to find it. All we're interested in is the observed output. But what if somebody had what if somebody had asked us to calculate x of t? Well, if we know x bar of t, we can calculate x of t by pre-multiplying with p inverse. So in this case, we take p inverse and we multiply it by x bar, which we just had. And now we can calculate x of t, which is going to be pretty complicated. So we take the first row, the second row, and the third row. We have a lot of fractions that we have to do, and this gives us our actual solution, x of t, in the original state space. So this is the time-varying response to that signal from an input delta of t. What's interesting now is that, again, we can take x of t and compute y of t. Y of t is equal to c times x. But c, as we saw before, is equal to 1, 0, 0. What this tells us is that we can take this same matrix that we had before, x of t, but it turns out we did a lot of work we didn't have to do, because column 2 gets rid of row 2 and column 3 gets rid of row 3. So what does this mean? Well, it means that after we actually multiply this out, we get the same time response for y of t that we had before. And that's actually important. This confirms the earlier result that we had for x of t and y of t. We just got to x of t a different way. And this should encourage you to think about why it is that we can have infinitely many states and still get the same output. So we can choose, as long as we have the same number of states, then we can choose x of t as we like and still get the same output c. Now there's a relationship between the different matrices, or the different rows and columns of A, or A bar, or A tilde, or A bar 3, however it is that you happen to choose A bar. And it has to have a different relationship to B bar, or B tilde, or B parenthesis, whatever you choose to call it. But we can have an infinite number of states that we pick to be our important states, if it turns out that we would like to have our matrix look a certain way to calculate e to the A bar t, or e to the A tilde t, however it is that you'd like for it to be.